tell us about the isodar injector.
So, yeah, my name is Jordan. This summer I worked with Professor Josh Spitz, working on the isodar experiment. So to start with some context, neutrinos are these very weakly interacting, highly relativistic particles. So they move very fast, very close to the speed of light. And they come in these three specific flavors. So they come in electron flavor, muon flavor, tau flavor. And the really cool thing that has been kind of discovered about neutrinos is that they can actually change between these flavors as they move throughout space in a process known as oscillation. So if you're looking at the standard model, you can find neutrinos living in the little lepton house with their electrons, muons, and tau friends. So on Earth, we can find neutrinos in radioactive decays and in nuclear reactors. They're actually the second most abundant particle in the entire universe. And so they're produced in a lot of different ways. So out in space, we see them in the nuclear fusion that occurs in stars. And then we can also find them being produced in really high energy events like supernova, black hole mergers, and even neutron star mergers, or kilonova. However, there's still a lot we don't know about neutrinos. And so previous neutrino experiments have found these mysterious anomalies in the data that they've recorded when studying the neutrino oscillation behavior. And so one possible solution to this issue could be introducing a new flavor of neutrinos called stereoneutrinos. This new flavor would not participate in any weak interactions, but it could interact gravitationally, which also makes it potentially a dark matter candidate. But we've yet to actually find direct evidence for these stereoneutrinos. So, enter the isodar experiment. Isodar stands for isotope decay at rest. The whole novel concept of this experiment is we want to take an accelerator and take it deep underground to our detector. So a lot of other neutrino experiments have your accelerator somewhere, you have your detector deep underground. For the first time, we're going to take our accelerator, put it underground with our detector. So the #1 science goal of isodar is we want to look and see if we can measure the neutrino oscillation patterns and distinguish between different models of neutrino flavors and see, is there a new stereoneutrino or is there not? And if there are stereoneutrinos, are there multiple? Are there one? And so, being a really sensitive experiment, we can also use this detector to look for new particles. A big one, we could look for dark matter in the form of axion-like particles. So, the way this experiment will actually work, we have our cyclotron, which is going to be accelerating H2 plus ions into beryllium-9 in the target. This makes the beryllium-9 release a neutron out into the sleeve, which is made of lithium and beryllium. The lithium in the sleeve will capture a neutron and turns it into lithium-8. Lithium-8, highly unstable, rapidly beta decays, releasing beryllium-8, an electron, and most importantly, an electron antineutrino. And occasionally this antineutrino can interact with one of the protons in our liquid scintillator detector. And when this happens, it will release a positron and a neutron, which we can detect in our detector as two different flashes of light. And we can use those flashes of light to reconstruct the properties of the neutrino and measure its oscillations, see if they're turning into other types of neutrinos or not. So at Michigan, our goal is to produce the actual neutrino source. MIT is working on the cyclotron, and the liquid scintillator detector is Dre's still kind of out on her. And so the way that we're actually going to be producing the source is through the lithium-beryllium injector. So the whole idea is we want to heat up lithium really hot and force it into a combination of lithium chips and powder. So we have to do this at a very high temperature, very high pressure, 2,500 psi. We also have to heat the lithium up to about 250 Celsius. And so this turned out to be a big engineering problem. And so we we have a number of different subsystems that we have to design and plan for in order to make this injector work. So we have a hydraulic system that needs to be designed, heating, actuators, vacuum, and gas. And so my main task this summer was to build the frame for the injector, and then also help plan and design the heating system and do a little bit of troubleshooting with the actuator system. So how we went about building this thing, we started by building individual faces on the floor, and then once we had assembled those faces, we were able to lift them up on the side and build the whole frame completely horizontal. And so once it was horizontal, we utilized a crane to lift and rotate the frame to get it vertical. This thing is insanely heavy, very dangerous if it falls on someone. So we had hard hats, a lot of safety, use the crane. So some of the other challenges we had with building were working with the 80/20 aluminum that this thing is made out of. And so the really fun task that I had when I got here was going through the 3D model and counting up all of the individual little nuts and figuring out exactly where they had to go so that we could feed them into the 80/20 before we started building anything. Because once this thing is assembled, we cannot put the nuts back in it. And so if we don't have the nuts, we can't screw anything in, can't do anything. We also had this big, heavy, 150-pound glove box plate that we also crane lifted in. That one was kind of a fun, unique challenge. Kind of had to rotate it, do some crazy things to get it to fit. We also had the typical delays in receiving parts that every experiment has. So moving on to the heating system, our engineer John came up with the idea to heat our injector in these 5 different temperature zones. So each zone is controlled by its own thermocouple, which will read the temperature of the heat tape that is heating it. The thermocouple will relay the temperature to the temperature controller, which literally just checks, is this temperature higher than what it needs to be? If it is, turn off the heat tape. If it's not, keep the heat tape running. And so my specific design tasks this summer were to calculate how much heat tape we actually need for this injector. And so once we calculated how much we need, we were able to calculate how much power that heat tape would draw, which is really important because if we don't have enough power to power this thing, it won't run. Another thing I kind of worked on was testing the heat tape that we already had, which was interesting because we found out that it does not at all work the way that they claim it should work. So that's fun, and now we have to go back and figure out, do we need different heat tape? So lastly, I also worked on a little bit of troubleshooting the actuator system. So what the actuators are actually doing is following the hydraulic system during an injection. So it'll guide the bellows down, and then once an injection is done, it'll pull the bellows back up. And so the actuators are being controlled by an Arduino, which speaks to a motor controller through I2C. I2C is a specific protocol between devices or controllers and devices. And so one thing we actually found out this summer was that I2C is a short-range communication protocol, which is not going to work because our injector is like 12 feet tall. So we figured out that we were going to need to introduce this I2C extender to the system. And so now our devices can talk to each other over much longer range. I think that cable is about 50 feet. And then the other big issue that we were troubleshooting this summer was we found out that our motors were producing a back current, which was crashing our Arduino. And so in order to protect our Arduino from the back current, we introduced an opto-isolator. So this is what the actuators actually look like. They're very slow. We'll put that in 2 times speed. You can see that there's a cantilever that is pulling pressure against the pressure sensor. And so the actuators are able to follow that change in pressure to follow the cantilever down, since in the actual experiment they'll be following the change in pressure from the injection and the lithium being smashed. So the future work that needs to be done on this injector firstly finish building it. It's a pretty big one. And so once it's actually built, we need to incorporate all the different subsystems that we're designing and creating. So incorporating heating, actuators, vacuum, hydraulics, gas, and also making enclosures for all of our electronics so that no one's walking by and like smashing into cores and ripping things apart. So we can just plug things into the little box. We never have to look at our electronics again. In the far future, the injector, once it's ready to go and tested and we make sure it works, we can ship it off to South Korea at Yemi Lab. These are actually the real caverns that are dug out in Yemi Lab for the target hall and the cyclotron. And so hopefully in the next decade or so, we can find some really cool new particles. So also just want to thank my cheerleading team for supporting me throughout the summer. So yeah, any questions?
You said that in the future you're shipping the injector to South Korea.
Yes.
I have two questions. One, how much does it weigh? And two, how are you getting it there?
That is a great question. It is very heavy. I think
Right.
there are multiple components that are like hundreds of kilograms, just individual parts that are inside the injector. And so I don't know exactly how we're gonna get there. It's a very big question. I don't know if either of you two know.
It's not so big on the grand scheme of things. The detector, which is going to have to be on site, right? This is 200 milligrams. Such things can ship.
So you mentioned that the sleeve had lithium and beryllium in it. Could you explain why there's also beryllium if it's just interacting with the lithium?
Yes. So the sleeve is a mixture of lithium and beryllium. In order for the beryllium in the sleeve, if one of the neutrons hits it, it'll create more neutrons. And so the more neutrons that are rolling around on the sleeve, the more likely that one of the lithiums will actually capture it. It helps ensure that more of these beta decays happen.
So when you talk about the heating system, at what temperatures are you going to heat it to?
We have to heat it up to about 250 Celsius.
I guess that's Spanish.
Yeah.
All right, thank you.